Okay, so this is a problem about Lewis structures for the week 4 problem in RPI Chemistry 1. And I am selecting the first two sets and trying to solve the Lewis problem. So the first problem is HIO3, and here I provide you with a periodic table. So the first job is trying to find out where's a hydrogen. Iodine is located right here, and then the oxygen is right there. So therefore, you are going to count the number of the valence electrons, and that's the first thing to do for doing this calculation. So A, HIO3, and valence electron numbers are 1, and iodine is right there, which is 7, right? 7th column, so 7. And oxygen, which is on the 6th column. So that's, but you have 3 of them, so 3 times 6. So that will make it 26 electrons. So you have a 26 electron essentially to make bonds and to be used as a lone pair electrons and to satisfy the Octet Rule and then minimize the formal charges. And so those are the things. So now I have this one in my hands, and then what you need to do is you want to put something other than oxygen or hydrogen in the center. So I'm going to put the iodine in the middle, and then I'm going to put an oxygen. There are 3, so I'm going to put it in oxygen here. Okay, just 3 here. And then I'm going to put on hydrogen next to the oxygen. So I'm going to choose the one on the right. So this is so essentially what I call quote-unquote sprinkle the atoms and putting some quote-unquote exotic atoms such as something that is not oxygen or not hydrogen, and in the middle, and then you just start to make connections. So first thing is I need to connect these two by the bond. So I need to use 4. So 4 bonds. So 4 bonds. I use them already, and from the valence shell electron, and each bond is 2 electrons, so that's an 8 electron. Right? And then I need to look at the, I can use a color if you like it. So I look at this, the case, I look at this oxygen on the top. I need 1, 2, 3, 4, 5, 6. Therefore, the one that oxygen there satisfies the octet rule. So does this one too. 1, 2, 3, 4, 5, 6. So you need to fill the electron outer and then start to filling inside. So outer first. So oxygen 1, 2, 3, 4. So those are the electron that is needed for lone pairs. So lone pair electrons. How many are they? 6, 12, and 4 more. So there's 16 electrons. So that's the first step and second step. And what's my third step is, okay, so 26, use them for the bonding and use to make a satisfy the octet rule. And then what you have left is what is inside of the iodine. And that was 2 electrons left. So I'm going to use different colors now. So this one turns out to be 2 electrons left. And so the last one is 2 electrons to the central, right? To the center atom. So we're going to put that one right there. So that will be everything satisfies the octet rule, and hydrogen is 2 electrons, so that's fine. And oxygen-wise, iodine-wise, everything satisfied. So this is essentially the octet rule satisfaction, and that could be one of the form of the Lewis structure. But there is one last one that you need to keep an eye on, which is number 5. And so this is sort of the step that you have to remember. So bond, lone pair, and then how many is into the center. Okay, and the last one is shift lone pair electron on oxygen if needed. Okay, so this is really the key portion of what's going on here. So let's look at this, what is called the formal charge situation. If you look at this oxygen with a bond with those three lone pairs, this one has a formal charges of -1. I think that this is one of the things that to expedite your formal charge calculation, it will be very useful for you to remember. Okay, and this one is actually can donate the electrons to form the double bond. By doing so, they can have their resonance form of double bond with those electrons. Okay, if you think about those oxygens, both are satisfying the octet rule. Left has 8 electron, the right has 8 electrons, right? The only difference is this one on the right has a formal charges of -1. The on the right do not have a formal charges, but you are enforcing the double bond on the other side. Okay, so that's the case. So if you look at now, let's start to look at the formal charges for the electron. Why this one has a formal charges of -1? Formal charges is oxygen. Oxygen is you need 6 electrons to be neutral. So you have 6 electrons. And then how many electrons do you have? Minus. You have a lone pair electrons. You have such a lone pair electrons number of lone pair electrons plus half of number of bonding electrons. Okay, so that's what people use. So 6 is a valence electron. How many lone pair electrons? 6. And half of this one has a bond. There's 2 electrons, so 2. This will make it 6 minus 7. There's a -1. They will make a -1 formal charges. So therefore, this one has a formal charges -1. This is a -1. Okay. What about the one in the middle? If you're looking at this one, this unit, I'm just looking at these atoms, then there are formal charges. If you look at that, formal charges, number of valence electron is 6, and then number of lone pair, there are 4, and half of bonding electron. There are 2 bonds, 4 electrons. So this means 6 minus 6, that's a 0. So this is actually neutral. It has no charges, no formal charges. So that's the other one. I mean, this equation turns out to be equally applicable when you're looking at the one at the top. So this one has no formal charges. Hydrogen, if you calculate that, that's no formal charges at all. So there are 2 ways to calculate the formal charges in the middle. And the one that I really like, this is actually a shortcut way for me to do. If you're looking at the overall formal charges, so let's look at the overall molecule. Right? This one says this one has no formal charges. That's what this one implies. It has no charges. It's just a neutral molecule. So overall, you have a formal charges of 0. The charges of this compound is 0. And I know this one is a -1. I know this is a -1. This is 0, and this is 0. So it's almost like -1 plus -1 plus x plus 0 and 0. If you want to put it as a calculation form, right? These are all the formal charges summation has to be 0, right? So therefore, x, which is a formal charges on here, right? The 1 must be +2. So that's really the shortcut way to balance it out. So I know that this one has a 4 more charges of +2 in the beginning, and that's for sure that I know. But that's a more like a shortcut way. For more, I guess, a conventional way is, let's look at the 4 more charges on the iodine. Okay, iodine, where are you? The 7th. The 7 is a valence shell electron minus how many lone pair electron? You have 2. And then half of 3 bonds, so 6 electrons. So 7 minus 5 is a +2. Right? So that's why it has a +2. So you have these cases where, if I shaded it, this portion is electron, there are too much electron localization, and this portion is there's too much electron delocalization. So this is the electron too deficient, and this is too rich. And the whole point of the shifting lone pair electron, particularly on oxygen, is very useful. This one, you want to remember this, and it's very useful. And that's the one that you can shift the electrons to neutralizing it. Okay, so I'm going to write it one more time. So what I mean by that is the following. So, you guys have done that. Make the bond. Put this all the lone pairs outside. You find that there's 2 electrons on the inside. And then you find out this is a -1, -1, and this is a +2, right? So this is this is essentially the same, okay? This is the same as above. And then what you can do is, like I mentioned in the number 5, shift the lone pair electrons. So I can start to think about, okay, why don't I choose this one and make a double bond here. And this one, by doing so, this side becomes now this with no former charges. Okay? And then now iodine is shown up here. Okay? And then what about the one at the top? Yeah, why don't I do that? I can reduce the former charges. By doing so, you can think about they are forming this double bond. And then there's no former charges for that. And then the remaining portion stays the same. Let's just think about that scenario. And so therefore, if you look at that, what about the former charges? Because the one that when you donate share the electron, lone pair electron in a form of an extra bonding, your former charges is reduced from +2 to +1, and there's one more, and the +2 becomes a 0. And so this one is actually the former charges on the iodine is going to be 0. And as I mentioned that, because everything is 0, the iodine has to be 0. That's the backdoor kind of shortcut way. If you want to do this one more time, former charges on iodine. Iodine means 7 valence shell electrons. How many lone pairs? You got 2. How many electron in the bond? You got 10 bonds. So that's 10 electron. You got 5 bonds. That's 10 electrons. So therefore, 7 minus 7 is a 0. So no former charges on the center. Okay, so do you have a choice to make? Either this one or this one on the top. Okay, the one that has a negative charges on the electron and positive former charges on iodine, or it can form this one as a double bond. And then the no former charges on this Lewis structure. So those are the 2 feasible Lewis structures. And then this one is too much charge delocalization. Okay? In other words, large former charges on the moon. Okay? What about this one? this one on the left. Somebody might actually wonder that, wait a minute, this iodine here is disobey octet rule, right? So that's not good. That's not really good. I mean, this is not good. Both are not good, but this one, the iodine in the middle, now let's have a look at it, where they are located in the periodic table. This iodine is located right here, which is like 1, 2, 3, 4, 5, the fifth row. So therefore, this one, though, because of the iodine is on the fifth row, extended octet rule can satisfy. So they can have more than 8 electrons. So for example, this iodine here, feel like having it essentially 10 bonded electron and 2. So it's like a 12 electron overall. It's a lot, but there's a lot of room for it because this one, you know, unlike those one in the second one, the maximum they can have is sp 2s and 2p. That's right. Do you remember the previous class? 2s, 2p, 2d. That's not possible. So only places that you can have is an 8 electrons, right? But this is the fifth row, so therefore 5s, 5p, that's for sure, but 5d, 5f, there is more rooms that this one can accommodate. Still, this is the octet rule is the one, but this is, they can kind of having a little expanded and more electron that can be accommodated because of the expanded octet rule. Anything with a third row and then higher, they can have a extended, or sometimes people call expanded octet rule. Okay, so here we go. So I just solved you with this first particular problem, and this HIO3 is a really well-known problem that people wants to solve it with you. Okay, so let me solve this H2CO3 problem in the next video.